three kinds of antiderivative problems that are not obvious at all. And they come from the inverse trig functions. A long time ago, we showed that the derivative of the inverse tangent function, for example, was 1 over 1 plus x squared. And so then immediately we said that means that the antiderivative of 1 over 1 plus x squared is the inverse tangent function. Okay? But I would like us to look at not 1 over 1 plus x squared, but 1 over a squared plus x squared, where a is just some constant. So maybe a is 3 or a is 5 or whatever. We've never seen this situation before. It was always 1 plus x squared. Well, I claim that the answer is kind of strange. It's 1 over a times the inverse tangent of x over a. Now, that's just my claim. Can I prove that this is the correct antiderivative? Well, hopefully, I can by just taking its derivative and see if I get what I started with. So I'm going to take the derivative of 1 over a times the inverse tangent of x over a plus c. So here I go. I've got a constant out in front. The derivative of the inverse tangent is 1 over, I did that up here, 1 plus, now I don't have x, I've got x over a squared, and then the chain rule says times the derivative of the thing inside, so 1 over a times x, the derivative of the thing inside would be 1 over a. The derivative of this constant, of course, that's 0. So I've got 1 over a times 1 over a, that's 1 over a squared. And in this fraction, I've got 1 plus x squared over a squared. Well, now if I distribute this a squared that's in the denominator, a squared times 1 is a squared, and a squared times this fraction, the a squares cancel, and sure enough, I end up with exactly what I started with. So there are actually 3 of these things, 1 for inverse sine, 1 for inverse tangent, and 1 for inverse secant. Now, most people have a hard time memorizing these, but you ought to add them to your list of antiderivatives. The one that we just did was the antiderivative of 1 over a squared plus x. Well, you know what? To even make this even more general, I'm going to call it u squared, where u could be thought of as a whole function of x, like when we do our u substitutions. We just showed that that's equal to 1 over this constant times the inverse tangent of u over a. Now we're going to do some examples in a minute, but I'm going to call that formula number 1. Formula number 2, very similar, 1 over, but this time it's going to be the square root of a squared minus u squared. Well, this time it's the inverse sine of u over a. And the hard part is there isn't a 1 over a out in front. when we take the derivative of this function, we get this function without having that constant out in front. That's kind of what makes these hard to remember. And then the third one comes from the inverse secant function. If we have u times the square root of u squared minus a squared, then just like the first one, it's 1 over a, but now it's the inverse secant function. And those weird absolute value bars. In most calculus textbooks, they have a whole table of derivative formulas, and they have a whole table of antiderivative formulas, and these are three that always show up in that table. So let me show you an example of a problem. So I'm going to keep that page handy, and we're going to look at this problem. The antiderivative of x over 9 plus x to the 4th dx. Now let me put this back down. The big question is, that problem, does it fit Formula 1, Formula 2, or Formula 3? And it's not a hard answer because Formula 2 and Formula 3 has these square roots in them. Formula 1 doesn't. I don't see any square root up here. This must be a type 1 problem. This must be my a squared. So a squared must be 9, which means a is 3. This must be my u squared. So u must be x squared. And out here we have to have du. Well, when you take the derivative, just like when we did u substitutions, the derivative of x squared is 2x, so du is 2x dx. So this problem looks like this, with a squared being 9 and u being x squared. But there's a little bit of a problem here because this denominator is 3 squared. This x to the 4th is x squared squared. But our formula says we have to have du up top, and du is 2x dx. We only have 1x dx. But constants we can take care of. So what you would do is supply the 2 and compensate with a 1/2. Now we have exactly what the formula says. We've got a squared, we've got u squared, and 2x dx, that's du. So our formula says our answer is 1 over a, and a is 3, times the inverse tangent of u over a plus c. Okay? You have to take these problems and make them look like the formulas. And whatever u is, you've got to make sure that you have du. So here comes a second example. Our second example is 1 over x times the square root of x to the 6th minus 4. Now I'm hoping you'll recognize that as being a type 3 problem. 2 and 3 both have square roots, but 2 says constant minus variable, and 3 says variable minus constant. We usually use the last part of the alphabet for variables, the first part of the alphabet for constants. So in all these formulas, a is a constant, u is a variable. So here's the formula. If you have u outside, u squared minus a squared inside, then it's this guy, it's an inverse secant. You got to remember to put the 1 over a out in front. You got to remember the absolute value bars of u over a. All right, well, let's see if we can fix this. If x to the 6th is going to be my u squared, that must mean that u is x cubed. And if u is x cubed, then when you take the derivative, du dx is 3x squared, so du is 3x squared dx. That's what I need to have up top, 3x squared dx. Ooh, I'm not even close. But if u is x cubed, I'm supposed to have u out here. So here we go with that creative algebra again. I'm going to multiply the bottom by x squared. And I can do that as long as I multiply the top by x squared. I need 3x squared for my du. So I'm going to multiply the top by 3, which means I compensate with a 1/3. Phew, I think I've got it now. Here is u. Here is u squared minus a squared. Evidently, a squared is 4, so a is 2. And if u is x cubed, du is 3x squared dx. It's fitting our formula exactly. So it's an inverse secant. We need the absolute value. We need u over a. We need 1 over a out in front. But remember, I had to supply that 1/3. So there's actually a 1/6 out in front plus c. These problems are not easy. It's hard to make the original problem fit the formula. Let me do one more example. And this time, it's going to be a type 2 problem. It's going to be the antiderivative of dx over the square root of 16 minus x plus 5 squared. Now, back to my formulas. I claim that that guy is a type 2 problem. Constant squared, variable squared. Constant squared, variable squared. This is going to be an inverse sign. Remember, on the inverse sign, there is no 1 over a out in front. My variable is u, which means that du dx is just 1, which means that du equals dx. Ah, well, we've got that. This is du, this is u squared. Here's a squared, so that means that a is 4. I don't have to do any work. This problem fits that formula exactly. Du over a squared plus u or minus u squared. The answer is the inverse sign. The inverse sign of u over a plus c. So when you look at these three formulas, it's important to keep track which one says which. The one that doesn't have square root in it, that's the inverse tangent. The one that says constant minus variable, that's the inverse sign. The one that says variable minus constant with the variable out in front, that's the inverse secant. The hard part is to figure out what u is and make sure that you've got du in there as well.